Hey, what's going on, everyone? Welcome back to Structure-Free Learning. And in this video, what we're going to do is go back to some engineering dynamics or physics and talk about kinetics of particles. And hopefully, by the time you've gotten to this video, you've had some background in kinematics, which is essentially the geometry of motion. We talk about position, velocity, acceleration of a particle. Um, and maybe you haven't covered rigid bodies yet, but and now what we're going to do is try to study some of the causes of this motion, which is really, the cause is really a force, right? And that's called kinetics, right? You look this up in Wikipedia and just see all what it has. And so in this video, I'll explain how Newton's second law is applied in solving dynamics problems. I'm not going to go through some derivation. I don't think I even know how to do it, but we'll just go talk about how we can apply it um, for our dynamics problems and use it the way we want to use it. And then I'll just display to you Newton's second law in various coordinate systems, and then hopefully maybe in another video or so we'll do a couple examples. But here, it all starts with Newton's second law, and dang, this law is amazing, right? It governs them all, right? It's the one equation that really has transcended the test of time. So, in the late 1600s, Newton came up with his second law of motion, which is that the sum of the forces here is equal to mass times acceleration. And when I see this equation, I really want to try to visualize a drawing. And here there are really two really important drawings. This first drawing here is I have this particle here. It's got all these forces acting on it, like F1, we'll say F2. And this particle could be anything, right? It could be a car, it could be a ball in the air, it could be, you just use your imagination of whatever you want it to be a particle, right? And here, this has all these forces acting on it. This I would call an external force diagram. External force diagram. And this is what you've called maybe from statics or somewhere else, your free body diagram. So this external force diagram. And what happens is when I apply this summation of all the forces, what I get is a resultant force acting on this particle here, which I will draw this way like this. I'll say the sum of all these ends up with this right here, this resultant force. And this resultant force causes inertia or a motion here. And we'll say here, this inertia is described by mass times acceleration. And the other drawing that's really important to make, in my opinion, is this inertial diagram. Inertial diagram. And being able to make these two drawings, bam, right here, will help this drawing and this drawing here in our problems will help you to solve all your dynamics or your kinetics problems in dynamics or physics, whatever class you're taking here. So here, that's how I look at it. Now, that's the one thing I like to do when I apply to solve these problems. But what's also important is now understanding, how do you break these up into the right coordinate system? And that's probably even more important in how we solve problems is choosing the right coordinate system. You could be given a problem. It's a particle moving on some path with all these forces on it, and it's got some acceleration. You're asked to find the velocity or something. And you have to find, and really one of the first things you have to do, besides drawing the free body diagram, is determine what kind of coordinates you're going to use and making these drawings, right? And so here, the coordinate system that you choose is equally challenging, if you will, to solve these problems. Coordinate system, right? So this is really important. And the coordinate systems that that we have dealt with really are there's only three kinds that we've dealt with in dynamics, or at least in engineering dynamics. So first course in engineering dynamics here, you would have dealt with Cartesian or rectangular coordinate systems. Cartesian or rectangular right here, or two, maybe a normal and tangential coordinate system. This might have been referred to as a local coordinate system, right on the particle itself. Or three, you might have dealt with a radial and transverse, okay? And what I'd like to do is show you what all this means right here. So if I have, for instance, a particle here, I'll just redraw it here. So if I have that particle here, okay, bam, my external force diagram or whatever, I have this resultant sum of the F here, and this was equal to mass times acceleration here. So I'll say bam, mass times acceleration. Now I can choose any coordinate system to solve this problem, this basic problem here. And one of the and let's say this thing is moving on a path like oh that'll be good enough. Okay. So we'll say we're moving on this path here like this. This particle is moving on this path here, that green line. And one of the first coordinate systems that you might use is a Cartesian coordinate system, or the rectangular Cartesian. Let's put that up here. We'll call that the Cartesian coordinate system right here. Okay, and the thing about the Cartesian or rectangular coordinate system is you need a reference, so we'll call that O, some reference, and you define a plus x and a plus y. And a lot of times people do it like either right on the particle or not right here. Okay, but you have a plus x and a plus y orientation. And what you do is you break up your component, this sum of the forces, into the x and the y components. Right here, sum of the forces in the x, bam, and sum of the forces in the y. And then you would also similarly break up this acceleration vector, or this inertial term right here, in max and may right here. And you know, technically you don't even need vector symbols or anything because you're looking one direction at a time. So some of the forces in the x when you're doing this problem in 2D is just max here, and then some of the forces in the y is may. And this is what, you know, is traditional. It's the easiest because you're so used to the x and y, you follow it a lot. And this is probably a lot of the places, a lot of times this is where people will go first to solve, you know, to come up with equations of motion, or these F equals ma equations. And you know, based on what you chose as the origins, these are your positive orientations right here. And this is one way you can approach the problem. Another way you could approach this problem is to choose an NT, or that normal and tangential coordinate system. If you choose NT coordinates, and here again, if I have the same drawing right here, so I'm gonna duplicate this drawing pretty quickly. Bam, bam. Let's go up here like this. And I have some, again, that sum of the forces, bam, MA, okay, right here. And I have, again, this path that it was going on, some path like this right here. And the NT coordinate system is defined, oh, anyway, whatever. The NT coordinate system was defined on the element or the particle itself here. And so here, the plus normal or plus tangential direction was tangent to the path, okay, plus t, or in the direction of increasing path. So if this was my velocity vector here, if my particle is moving generally this way, and this velocity vector is tangent to the path at that point, here's my plus t. And my plus n direction was defined as towards the center of curvature of wherever that particle is, plus n right here. Bam, let me give it some more, plus n right here. And then here I would make that same drawing over here. This would be that plus t, and this would be that exact same plus n right here. And now I would just break these up into appropriate components. This would be sum of the forces in the n direction. I'd have a sum of the forces. Oops, let's do that a little bit more precisely. So I'd have a sum of the forces in the tangential. And here I'd have a MAT and an MAN here, okay? And I just go through and I you know, again, summation of all the forces in the N is equal to MAN. Summation of forces in the T is equal to MAT right here. And this, if you remember what the normal acceleration was in NT components right here, this was m v squared over rho, where rho is the radius of curvature, and then this m was dv dt. And this coordinate system had the specific advantage so that when you looked in the tangential direction, it looked like 1D motion. And then you had the centripetal component right here. The centripetal acceleration was often, that's what this v squared over rho was sometimes called right here. But this is it. This is what you would use if you, this exact same problem, exact particle in the exact same motion, but in NT components. And then last but not least, you could attack this exact same problem in radial and transverse, or what sometimes people call polar coordinates in 2D, right? Or cylindrical in 3D, right here. But here again, if I have the exact same particles, exact same drawings right here, this right here, my sum of the forces, bam, like this, uh, mass, the inertial term like this right here. And now, just like the Cartesian coordinate system, the radial transverse also needs an origin. And so here, let's say here's this path here that this was traveling on, right? And here I have this origin here. Here's my origin of that coordinate system. My radial direction is defined as from the particle. My positive radial direction is defined as from the origin to the particle. So there's a line here, if you can envision a line going like this. And so this is my plus r direction. And my plus theta direction, okay, my plus theta direction is 90 degrees to the r. So here in going counterclockwise. So this would be my plus theta orientation. And so same thing here, for this exact same particle right here, I have my established my plus r, or my plus radial direction, and my plus theta in the 90. And these two drawings are exactly the same, other than that this is the inertial term over here on MA, and this right here is the external forces on this left side right here. And again, you just break up into components, right? So here you have the sum, bam, this would be my sum of the forces in the radial direction, sum of my forces in the transverse right here. And then same thing here, my inertial term in the radial direction and my inertial term in the transverse direction right here. And then I go ahead and I apply the equation, Newton's second law, or the equation of motion in each direction. Sum of the forces in the r is equal to MAR. Sum of the forces in the theta is equal to MA theta right here. And if you remember the substitutions for acceleration, this the acceleration was r double dot minus r theta dot squared, where theta dot was the angular velocity and r double dot is the acceleration in the radial direction. And then here this was r theta double dot plus 2r dot theta dot. Again, where theta double dot is the angular acceleration and theta dot is the angular velocity. So this is essentially it. These are the three forms, or the three coordinate systems that are used, or that you should use, to solve all your Newton's second or kinetics problems in engineering dynamics, or some course in classical mechanics and physics, whatever you're taking, right? Anyway, so hopefully you enjoyed this explanation. Maybe it was a bit longer than needed, but it is what it is. And let me know if you have any questions. Enjoy. See ya.